Hello and welcome to electromagnetic waves in guided and wireless media MOOC course. In the previous modules we were discussing channel models. We restricted ourselves to very simple channel models as the course is not sufficient, as one or two lectures is not sufficient to cover the various aspects of wave propagation in different types of channels and especially the wireless channels. There are a lot of secondary effects such as multipath fading that we have not touched upon, and those things take us slightly out of the electromagnetic wave nature and to consider the detailed environment and other things. Therefore, we have avoided that. However, we did see a simple two-ray model and then we calculated what is called as break point. As you monitor the power that you measure as you move away from the base station antenna, you see that the power of course drops, and this power drop would initially be around 20 dB per decade as predicted from Free's transmission formula that we have seen earlier. However, in reality in urban centers this drop will be, instead of minus 20 dB per decade, it would be more than that, it would be minus 30 dB per decade on an average. And then after the break point is reached, beyond the break point the slope actually changes over to minus 40 dB per decade. So, clearly this on an average this this type of power changes or power variations as you move away from the base station antenna can clearly limit the range of the useful service area of the base station antenna. So, if you go beyond that, then you need to have one more base station antenna. So, in fact, this is the basic idea of dividing the geographical area into number of cells, so that each cell is served by a base station antenna, and as you move from one cell, of course, its cells are not marked in border areas or something like that. These are mostly dependent on the, or these are mostly defined on based on the abstract notion of a cell that divides up the region of cells, mobile services that we are talking about. So, there is no fences around the cells, but it is rather the conceptual idea that as you move away from the base station antenna, the power is going to drop, and once the drop becomes so much, that is the power drop becomes so much or the attenuation becomes so much, then that our receivers will not be able to detect any more power, which of course is necessary for us to demodulate the information that is being transmitted from the base station antenna to the mobile antennas or mobile receivers. So, when that cannot be done, that is when the power drops below the minimum specified power levels or the sensitivity of the receivers, then that would be considered to be the edge of the servicing part, right. So, we have seen that this long term average thing is, or long range power loss or attenuation is one phenomenon of that one, and then we saw that around this long range on an average power variation, there could also be variations as you move from one part of the center an urban area or semi-urban area to another part of the center, and this happens more frequently in the urban areas because of the trees, buildings, poles and any other big obstacles that are present. Okay. So, the effect of this is sometimes the signal would gain, sometimes the signal would be lost, and so in some sense there would be variations around this long range or long range attenuation that we have seen. On top of that diffraction effects or what is called as shadowing losses, there could be minor changes as you move over a wavelength range or couple of wavelengths range, and that minor changes in the or rather those are major, but those dynamic changes which actually happen as you move very closely away from the in terms of certain wavelengths from any given position is called as multipath fading. So, we have seen all that, and we have seen that breakpoint analysis can also be developed. What we have not seen and what we have just mentioned is this phenomenon of shadowing, right. Shadowing is something that is very familiar to you. So, you are talking to your friend or you go behind a exit a building or just go behind the building, immediately the signal drops, right, and in some extreme cases you can keep saying hello, but the other person does not receive anything, clearly indicating that the communication path has been broken, right. So, what this is called as shadowing, and this is one of the most prominent effects of urban mobile communication systems, right. So, in order to overcome this shadowing, either one has to place more base station antennas so that the coverage is more, which of course has its own problems in terms of health hazards, in terms of regulations and in terms of simply people refusing to let their areas rent out to put more towers. So that is a problem that is associated with that. The other way is to really understand why this loss is occurring and possibly can we do something about that. Okay. So maybe one can actually have in a region of big buildings or in a group of labs or an institute these smaller antennas which kind of interface with the main or the base station antenna, catch a portion of the signal and then serve as hot spots, right. So, like not exactly the hotspot that you are familiar with, where you put the wireless routers and other things, but these hotspots are made out of small miniature antennas which serve no more than a few feet, right. So, this way one can, I mean, in order to even do that and where to place this antenna and other things, you need to understand this phenomenon of diffraction which is actually causing the gain variations to occur, right. So, in order to understand that, what we are going to do in this and possibly in the next module as well is to study this phenomenon called diffraction. Now, please do not infer from whatever we have said that diffraction is only limited to understanding of wireless channels. Absolutely no. Diffraction shows up in places in everywhere wherever there is electromagnetic wave involved. In fact, it shows up even in places where acoustic waves are involved. Okay. This goes under the general name that electromagnetic waves or light waves bend around the corners, right. I will come to that one in a moment or so, but this is a phenomenon that you must have you have seen, and if you have not seen, what you can actually do is squint your eyes towards any light source. Okay. So, just try to close your eyelids, not completely, of course, when you close it completely you will not see anything, but you just close it such that you are seeing some amount of light. So, as you close, what you have created, this small area that you are seeing is what is called as an aperture. Aperture is a fancy term for an opening. Okay. So, what you have done by closing your eyes to or bringing your eyes closer to each other, the upper this thing is that you have just letting light pass through this small aperture. Now, from high school physics you have been taught that light is ray and rays pass through in a straight line, and if there is an opening then light will actually pass through that opening and everywhere else it would be black, right. So, if you imagine that you have some sort of an aperture here, okay, and then light which is light source which is kept far away from this, then what you expect on a screen that you would place at the back would be that, please note that this is the aperture. So, outside this aperture whatever we have is all opaque screens, right. So, you of course, you will not see it in this way, you would see it in this particular manner. So, you may imagine that you have an opaque screen or an opaque block or something, and then there is a small opening here. I have shown the opening to be quite large, but this opening should be just about few wavelengths of order. Okay. It should not be too high, rather it should not be too much, too wide, then you will not be able to observe this effect, right. So, as you squint your eyes and then look at the light source, this is what you are actually doing. So, there is a squinted eye, light source is somewhere kept on the wall quite far away, a few feet away, and then that light rays would travel through this aperture, right. So, from whatever we have learnt in high school physics, if that was true, then let us assume that the light rays are essentially uniform plane waves that are coming through us, and these rays, as this the central ray would of course pass through as it is because it is not seeing any obstacle on this side. However, what you would expect is that the edge rays would simply transmit through this one, right. In fact, this region is what we call as shadow region, right, because no light is supposed to pass here, and if you measure the width of this aperture, or rather if you know the aperture width to be a, then the light width would also be exactly equal to a, is what the geometric optics from high school physics would tell us. Okay. However, in practice what you would see is that these rays do not essentially remain in that manner, but they kind of spread out from this. So, where you did not expect any light, so this was no expectation of light, right. There was no expectation of light because we assumed naively that the rays would actually, the edge rays would actually propagate in a straight line and they would hit this particular observation screen, and whatever this one would also be, I mean all these things would have been the shadow region, right. Earlier this would have been the shadow region, but unfortunately that is not true. There will be light in this region. In fact, if you can afford an extremely sensitive light, then you can also observe some amount of light here, because this width, and of course, if you move this away, not at the given position. So, if you move this position away to a new screen that you can put somewhere at a further distance from this, then you would actually see that light spreads out even more. Okay. So, in some sense, if you consider this as earth and this as moon, right, and you want to observe moon by sending light, then if you send in this kind of an ordinary light, the diffraction effect, because the distance between earth and moon is so large, the diffraction effect would actually move, or would create a spot of light which is very wide, perhaps as wide as moon, and as the beam size increases, the energy that you would see at on a particular patch of intercepting this particular electric field or the light wave would be very limited. This is just like an antenna, right. So, you have an antenna whose radiation pattern you can imagine keeps going wide and wide, and if you have a receiving antenna that is only so much, then it will impact, or it will perceive only part of this light source, and because light as it spreads out, it has spread out its energy in a wider range. So, when you probe only a small area, you will actually see very little amount of light being intercepted. This is in fact the concept of effective aperture that we have already talked about in the context of an antenna. Okay. So, there is also a very close relationship between diffraction phenomena and antenna radiation pattern. Perhaps if you take up a course on antennas, you will discover this relationship. The basic idea is some antenna patterns can be considered to be diffraction patterns. Okay. Not all antennas, some antennas, those antennas are called as aperture antennas. Anyway, coming back to our discussion, the basic idea is dispersion causes the beam to actually spread out. Okay. So, this spreading out phenomena is creates light where there was no light to begin with, right. So, this phenomenon is called diffraction, and we want to understand this diffraction. So, we will turn to some simple models of diffraction, because the subject, although originated mainly in the context of light, and it was used as kind of a precursor to tell us about light phenomena that cannot be explained by the usual corpuscular theory, which was quite popular during Newton's time. So, when they tried to explain diffraction, they just could not explain diffraction based on the corpuscular theory. However, wave theory was invoked, and wave theory was actually useful in explaining this. You must probably have heard of what is called as this Huygen principle, which says that light incident at every point on this aperture would actually be equivalent of creating small secondary waves, and these waves would then go away in this particular manner, and these waves, when they intersect at a screen, will create the complicated diffraction, or rather they will complicated interference, they will create the diffraction pattern. So, this phenomenon is called as Huygens principle, sometimes Huygen is also spelled out as Huygen. So, either way, the person was actually responsible for a lot of interesting work during the early optics area, and this thought of, or this ideas of spherical wavelets and secondary waves producing further waves was basically because of this person. However, Huygens ideas were put on a firm mathematical or reasonably firm mathematical foundation by this well known scientist whom you have heard in terms of circuits laws as well, called Kirchhoff. And this Kirchhoff-Huygens theory of diffraction was kind of quite useful, or this one. Of course, the first person to do this was Fresnel, and then Fresnel-Kirchhoff or Fresnel-Kirchhoff ideas were kind of the first mathematical steps to put this Huygens principle on proper mathematical basis, and later this was amended by a person called Sommerfeld. Okay. So, today we use this Sommerfeld diffraction integral to understand the effects of diffraction. Okay. Anyway, the goal is not to derive this, because this theory is very complicated, and although as I said it originated in the context of light and understanding the effects of this light phenomena, it turned out that it is very difficult to solve diffraction problems when light is involved and apertures are involved, but rather comparatively it is easier to understand this phenomena in the acoustic waves. And a person called Lord Rayleigh, a scientist called Lord Rayleigh, who also won Nobel Prize, did a lot of work in acoustic wave diffractions. Okay. So, he published a very good textbook called as The Theory of Sound, and if you get an opportunity to read that one, you will read how sound waves can be analyzed and how sound waves diffract, and all those curious phenomena of sound considered as a wave was actually derived, most of it was derived by Rayleigh, Sommerfeld and these guys, and Rayleigh's work is especially, I would recommend it if you get an opportunity to read that one. Okay. So, what we are going to do is to kind of get to Sommerfeld integral or Kirchhoff-Sommerfeld diffraction integral, but without going through too many mathematical steps. Okay. So, yeah, before we go to that, I would like to mention this point, and which I have, of course, I have mentioned. So, if this aperture opening was A, or the radius of this one was A, or the width of this one was 2A, then this spot from geometric optics would predict that it would be A, but wave would predict that it would be actually greater than A, right. So, because that is the whole point of this diffraction. So, while we would have thought that in the shadow region there should be no light, but that strictly speaking it is not really so. And coming to Huygens principle or Huygens wavelet, what he assumed was that everywhere light is incident on this aperture, it would actually create a spherical wave, okay, or a spherical wavelet, and spherical waves are given by they are dependent only on the radial direction, that is, as you move away their amplitude decays, and we call this a spherical wave because with some amplitude, let us say psi 0, they exhibit two phenomena. One would be the amplitude decay in terms of 1 over r, and the other one would be the phase change, which actually occurs as e power minus j k r, right. So, the k r is the phase term. Of course, I am using the phasor notation. The correct expression would perhaps be psi of r t real part of psi 0 by r e power j omega t minus k r, correct. So, this is what the correct expression for the electric field would be, or the magnetic field. See, we have made one major assumption here. We have discarded the vector nature of the light. We do know, of course, that light consists of electric field and magnetic field, and the proper way to address light, especially light propagating in free space, would be to actually think of light as a vector field, right. However, the vector diffraction theory is much more complicated than the corresponding scalar diffraction theory, okay. So, we will not consider the vector diffraction theory. We will assume that we can represent light that is falling on the aperture, or light propagating, or the base station antenna transmitting a certain radiation. All these electromagnetic waves can be described in the context of diffraction as some simple scalar fields, okay. So, we are ignoring the vector nature of this, but the assumptions or the approximations that we make are not so strict. Most of the diffraction phenomena can still be explained in the context of scalar diffraction integrals. So, that is why we have chosen the scalar, and we have chosen a new variable psi, because the psi could be Ez, Hz, Ex, Hz, any of those components. It could also be Er, Hr, all those components it could be. So, I am representing everything collectively as a scalar psi of r. And as I have said, this is in the phasor domain, this is the real time domain, or rather the time domain waveforms that you are actually looking at, or the fields that you have. We will work with phasor domain, so that I do not have to write this real part as well as this e power j omega t part, okay. So, this is called as a spherical wave. Why is this called as a spherical wave? Because if you interpret this as electric field, then the power density of this one would be proportional to magnitude of the electric field square, right. So, it would of course be E cross H. However, in the scalar approximation, H is kind of psi of r, E is also psi of r. So, therefore, and because psi of r is a complex number and energy has to be a positive quantity, so we just take the magnitude square. So, when you take the magnitude square, the phase term will of course drop in, but this psi of r magnitude square would actually be psi 0 magnitude square divided by r square, right. So, now if this is the wave which is actually falling, the power is falling as 1 over r square, the overall power will be what? Power will actually be constant. Remember, power will be obtained by integrating this one over the solid angle d omega, right. And when you integrate this one, r square and r square here will cancel. So, there is some sin theta, and d omega is basically d theta d phi. Actually, d omega is r square d theta d phi. I have just kind of written this r square explicitly, show that this r square can cancel out, and this quantity, assuming that this psi 0 is independent of sin theta, then this would actually be a finite value, right. So, remember, theta goes from 0 to 90 degrees, not 0 to 80 degrees, and phi goes from 0 to 2 pi, right. So, the power density goes down as 1 over r square, but the power itself stays constant, right, and this is the first assumption of Huygen. So, we are going to erase all this. What I am interested is to let you know that this is a spherical wave, and once we understand that this is a spherical wave, we can go on to the next step, okay. We will assume first of all that the source itself, which is placed at some point, itself emits a spherical wave. Okay. So, I mean this is also okay, because we have considered the source to be very far away and we assume that the source itself is going to emit a spherical wave. So, in effect what we are assuming is a point source. Okay. So, we are assuming a point source. If you do not assume a point source, but then you assume that the electric field or the light wave could actually be given by a certain point P, right, in the xy plane. So, this is the xy plane that I am considering. So, this is on the xy plane. At this point we will consider the source. I am not assuming source to be a point source, we will later on make that assumption, but the development of the theory will be slightly easier if I do not make this assumption. Okay. So, this is a source and these are all the points, right. The source actually has a certain finite extent. So, the source has a finite extent and I am considering the source the part of the light that is being emitted at this point which I have labeled as point P. Okay. Far away here is where my aperture is located. Okay. So, I have this aperture here which I will draw it. I have only indicated, I mean I am indicating a circular aperture, but that is clearly not limited to a circular aperture. Okay. So, this is my aperture which I will call as A, and there is a straight line which you can draw which goes from point or rather there is an origin for this aperture in that particular z plane. So, this is a constant z plane. So, clearly this would be some x axis, this would be some y axis, and the plane that I have plotted here is also similar. It is an x axis y axis plane, but the distance between this origin to this origin would be different, and from the distance between the source point onto the origin can be given and indicated as r. Okay. So, by indicating this as r or rather r0, I will indicate this as the distance from the point of the origin on the aperture plane onto the point of the source which I am considering here. So, this is the part of the source. Of course, there will be some portion of source here, portion of source here, here. These are all potentially points that I have to consider. I have made it slightly generalized in the sense that I am only considering the point at this particular thing. Okay. So, at this point there will be a spherical wave. So, you have to imagine that there is a spherical wave, and if I consider a point q here on the aperture and indicate that q has the coordinates x0, y0 and 0. Remember, I am considering this as a constant z plane. So, I can take this plane to be at z equal to 0. Okay. I will also further assume that the radius of the aperture A is very small compared to the distances that are involved. So, initially the distance that from the point P onto the z plane where the aperture is located, we have indicated this to be r0. So, we will assume that this A to be much smaller than r0. So, essentially looking from the position of the source and onto the aperture should look very small. Okay. It should look like a very small opening. It should not look like a big cave and you have a source which is very small like a laser pointer here. No, that is not what we are looking at. What we are looking at is in this other way around. So, you have a light source which is decent enough, but the aperture is very small. Okay. So, that is what we are looking at, and I have indicated the point Q on the aperture because the light from point P would reach point Q here. Okay. This distance of course is r. You know that this is the r value is the one that actually matters, because the spherical wave may actually begin to emanated from point P. The amount of attenuation that the wave would undergo would actually be given by this distance PQ, which we have indicated by r. Okay. Incidentally, P would be identified by the coefficients which we will call as coordinates which we will call as xs, ys and perhaps zs. Okay. Meaning that this is located at that is this plane is located at zs equal to constant or z equal to zs. Okay. So, the distance PQ is r and the distance PO is r0. So, these are all up to the source point. Okay. Now, we will imagine that I am going to go to another plane which of course would still be at the xz plane, but at this plane I am going to consider the field point and label it as P prime, and then I will have the same x and y directions that I have indicated. So, this plane would be located at plane of z, and the coordinates of this one, this point P prime will be x, y and z. Okay. From the origin O of the aperture, if you go to a point P, so the distance OP prime we will call it as S0, and because light has been now incident on point Q, you can imagine that there is a small area around point Q which has a area which we will designate it as d sigma, okay, and this d sigma corresponds to the infinitesimal area from which the part of the spherical wave that has been incident on Q would then begin to propagate and reach the point R. Okay. So, I am going to write down this point from the point where the light source has been incident Q. So, please note that these should have been straight lines, but on this board I am not able to draw them correctly. Okay. So, we will call this distance as S0 and we will call this distance as S. Again we ask that this A be very far away from this S0 or equivalently S. Okay. This assumption that the aperture looks very small located from the source as well as from the object or the field where we are looking at is what is called as Fraunhofer limit. Okay. And the corresponding diffraction is called as Fraunhofer diffraction. There is a different formula which we will develop shortly, which actually gives the limits of where the Fraunhofer diffraction typically begins. Okay. But for now this is our geometry, and the basic idea of developing this Fraunhofer diffraction integral or simply the diffraction integral is to recognize three things, right. First, the source at P prime would actually generate a spherical wave which would propagate and land at psi of Q. Okay. From psi of Q there will be a secondary wave which is also spherical wave. So, this is also spherical wave, and psi of Q would also be a spherical wave. With this spherical wave as the kind of an input in some sense, you will then land up with the field at the point P prime. Okay. Psi of P was the source point and then psi of P prime is the field point. Okay. So, the source point which is kept at xs, ys and zs, right, in that particular point would first emanate a spherical wave and then you would land up with that spherical wave at point Q. From point Q you would again have another spherical wave because of Huygens principle, and then it would land up, the amount of certain thing would the spherical wave would part of the spherical wave would land up at point P prime, which is defined or which is given by the coordinates x, y and z. Okay. You could of course observe two things, right. One, we have neglected the obliqueness factor from P prime to Q, that is we have not yet written that, but we are going to neglect it in the sense that whenever I write this P prime to Q, the direction of that P prime Q vector or the line must also be taken into account, because P to Q and of course Q to P prime, that is the second same observation, they will be different if you go to a different point. For example, if this is my other source, then from P to Q the direction of this line will be different from the direction of this one, right. So, you can clearly see that these directions are different, and this factor in both source to the aperture and aperture to the observation plane has been neglected, and this is called as the neglecting the obliquity factor. Okay. The fact that source and fields could be oriented in different directions is being neglected. Since this is coming to an end, this module, we will of course continue this work in the next module. I will then tell you another assumption that we are going to make, which would simplify our analysis. Thank you very much.